Hi everybody, this is Oliver and Lingfeng representing the finite element analysis on bike frame dynamic behavior. As people riding bicycles, the bicycle frame will sustain majority of the loads from various scenarios, such as frontal load, drop load, and back load. And here are some facts and benefits of conducting FEA on bicycle frames. In this project, we're going to use UGNX and ANSYS to design and analyze the given bicycle frame with three designs. First, lightweight steel, second, moderate weight steel, and third, moderate aluminum alloy. Let's talk about the CAD drawing of the first design. Here are some of its specifications. It is important to notice that the thickness of the tubes that are connecting other thinner tubes at joints is in 5 mm, and the thickness of the other tubes is in 2 mm. This is the lateral view with detailed dimensions. And this is the top view. And this is the front view and the back view.
This is the information mesh, and we assume the person rides a bike, so there are forces on middle tube and handle. For frontal impact, we put 440 newtons on frontal pipes and fix the back tube. It's the total deformation distribution after analysis. The maximum is here, which is 31 mm, and for stress, the maximum is here, which is around 700 megapascal. For drop load, based on Valhalla, the drop force is 3 times weight of bike, which is 82 newtons applied here, and we fix the front and the back tubes. And it's the figure of total deformation distribution. The maximum is here, which is 0.86 millimeters, and for stress, maximum is here, which is 150 megapascal. For back impact, we assumed a car hits the bike and applies 440 newtons on back tube, and we fix the frontal tubes. After doing analysis, the maximum deformation is here, which is 87 millimeters, and for stress, the maximum is here, which is 1800 megapascal.
Additionally, we analyzed the resistance to fatigue and the associated safety factor as shown below. From these graphs, we can see that the frame will have the highest resistance to fatigue in the drop load scenario. When there's a load applied from the back, the frame is most likely to fatigue and buckle because it had the smallest safety factor. For the second design, we changed the thickness of the tube as section 1 and 2 shown down below from 5 mm to 8 mm. And we also changed the thickness of the tube as section 3 to 6 and the thickness of the fork as section 1 and 2 from 2 mm to 5 mm.
After changing geometry, the numbers of elements are around 34,000, and all assumptions didn't change. For frontal impact, the maximum deformation becomes around 20 millimeters, and the maximum stress is 855 megapascal. The drop load is 176 newtons because the mass is changed. And its total deformation distribution, the maximum is here, which is 0.87 millimeters, and for stress, the maximum is here, which is 154 megapascal. And same conditions for back impact. And then we use aluminum to analyze some geometry. It's a total deformation distribution. The maximum is here, which is 71 millimeters, and for stress, the maximum is here, which is 206 megapascal. For frontal impact, the maximum deformation is here, which is 56 millimeters, and for stress, the maximum is 850 megapascal. For drop, the maximum deformation is here, which is 2.4 millimeters, and for stress, the maximum is 154 megapascal. For back impact, the maximum deformation is 200 millimeters, and for stress, the maximum is 2000 megapascal.
In conclusion, we can draw a comparison of the basic properties of the two materials from these tables. So based on the results shown previously, in this table we can see that thickening the steel tube and making the frame heavier does make it more sustainable. However, if you apply aluminum to the frame with thicker tubes, the frame will still be weaker than it is in the lightweight steel design.